Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 152, How We've Overestimated Few-Shot Learning Capabilities, published on the 16th of June 2021 by Rohin Shah. Highlights. Link True Few-Shot Learning with Language Models by Ethan Perez et al., summarized by Rohin. We can get GPT-3 from newsletter 102 to perform useful tasks using prompt programming, in which we design an input sentence such that the most likely continuation of that sentence would involve GPT-3 performing the task of interest. For example, to have GPT-3 answer questions well, we might say something like, "The following is a transcript of a dialogue with a helpful, super-intelligent question-answering system," followed by a few example question-answer pairs, after which we ask our questions. Since the prompts only contain a few examples, this would seem to be an example of strong few-shot learning, in which an AI system can learn how to do a task after seeing a small number of examples of that task. This paper contends that while GPT-3 is capable of such few-shot learning, the results reported in various papers exaggerate this ability. Specifically, while it's true that the prompt only contains a few examples, researchers often tune their choice of prompt by looking at how well it performs on a relatively large validation set, which of course contains many examples of performing the task, something we wouldn't expect to have in a true few-shot learning context. To illustrate the point, the authors conduct several experiments where we start with around 12 possible prompts and must choose which to use based only on the examples given, typically 5. They test two methods for doing so. 1. Cross-validation. Given a prompt without examples, we attach 4 of the examples to the prompt and evaluate it on the last example, and average this over all possible ways of splitting up the examples. And 2. Minimum description length. While cross-validation evaluates the final generalization loss on the last example after updating on previous examples, MDL samples an ordering of the examples and then evaluates the average generalization loss as you feed the examples in one by one, so more like an online learning setup. On the Llama UHN task, the difference between a random prompt and the best prompt looks to be roughly 5 to 6 percentage points, regardless of model size. Using MDL or cross-validation usually gives 20 to 40% of the gain, so 1 to 2 percentage points. This suggests that on Llama UHN, typical prompt-based few-shot learning results are likely 3 to 5 percentage points higher than what you would expect if you were in a true few-shot setting where there's no validation set to tune on. But it may actually be worse than that. We've talked just about the prompt so far, but the validation set can also be used to improve hyperparameters, network architecture, the design of the learning algorithm, etc. This could also lead to inflated results. The authors conduct one experiment with AdaPet on superglue that suggests that using the validation set to select hyperparameters can also lead to multiple percentage points of inflation. Rohin's opinion. The phenomenon in this paper is pretty broadly applicable to any setting in which a real-world phenomenon is studied in a toy domain where there's extra information available. For example, one of my projects at Berkeley involves using imitation learning on tasks where there really isn't any reward function available, and it's quite informative to see just how much it slows you down when you can't just look at how much reward your final learned policy gets. Research becomes much more challenging to do. This suggests that performance on existing imitation learning benchmarks is probably overstating how good we are at imitation learning, because the best models in these situations were probably validated based on the final reward obtained by the policy, which we wouldn't normally have access to. Section Technical AI Alignment. Subsection Technical Agendas and Prioritization. Link High-Impact Careers in Formal Verification, Artificial Intelligence, by Quinn Doherty, summarized by Rohin. This post considers the applicability of formal verification techniques to AI alignment. Now, in order to verify a property, you need a specification of that property against which to verify. The author considers 3 possibilities. 1. Formally specifiable safety. We can write down a specification for safe AI, and we will be able to find a computational description or implementation. 2. Informally specifiable safety. We can write down a specification for safe AI mathematically or philosophically, but we will not be able to produce a computational version. And 3. Non-specifiable safety. we will never write down a specification for safe AI. Formal verification techniques are only applicable to the first case. Unfortunately, it seems that no one expects the first case to hold in practice. Even Chai, with its mission of building provably beneficial AI systems, is talking about proofs in the informal specification case, which still includes math, on the basis of comments like these in Human Compatible, and there's a link. In addition, it currently seems particularly hard for experts in formal verification to impact actual practice, and there doesn't seem to be much reason to expect that to change. As a result, the author is relatively pessimistic about formal verification as a route to reducing existential risk from failures of AI alignment. Section Learning Human Intent. Link Navigation Turing Test, NTT, Learning to Evaluate Human-like Navigation, by Sam Devlin et al., summarized by Rohin. Since rewards are hard to specify, we're likely going to have to train AI agents using human feedback. However, human feedback is particularly expensive to collect, so we would like to at least partially automate this using reward models. This paper looks at one way of building such a reward model, training a classifier to distinguish between human behavior and agent behavior, i.e. to be the judge of a Turing test. This is similar to the implicit or explicit reward model used in adversarial imitation learning techniques, such as GALE or AIRL, both from Newsletter 17. Should we expect these classifiers to generalize, predicting human judgments of how human-like a trajectory is on all possible trajectories? This paper conducts a user study in order to answer the question. Specifically, they have humans judge several of these Turing tests and see whether the classifiers agree with the human judgments. They find that while the classifiers do agree with human judgments when comparing a human to an agent, i.e. the setting on which the classifiers were trained, they do not agree with human judgments when comparing two different kinds of artificial agents. In fact, it seems like they're anti-correlated with human judgments, rather than simply having no correlation at all. Only one of the 6 classifiers tested does better than chance, at 52.5%. The median is 45%, and the worst classifier gets 22.5%. Note, however, that the sample size is small. I believe n equals 40, though I'm not sure. Rohin's opinion. Ultimately, my guess is that if you want to predict human judgments well, you need to train against human judgments, rather than the proxy task of distinguishing between human and agent behavior. That being said, I do think these proxy tasks can serve as valuable pre-training objectives, or as auxiliary objectives that help to improve sample efficiency. Subsection Forecasting. Link Excerpt Episode 7.5, Forecasting Transformative AI from Biological Anchors, with Daniel Phelan and Ajay Kotra, summarized by Rohin. This podcast goes over the Biological Anchors framework from Newsletter 121, as well as 3 other approaches from Newsletters 105 and 145 to forecasting AI timelines, and a post on aligning narrowly superhuman models from Newsletter 141. I recommend reading my summaries of those works individually to find out what they are. This podcast can help contextualize all of the work, adding in details that you wouldn't naturally see if you just read the reports or my summaries of them. For example, I learned that there's a distinction between noise and effective horizon length. To the extent that your gradients are noisy, you can simply fix the problem by increasing your batch size, which can be done in parallel. However, the effective horizon length is measuring how many sequential steps you have to take before you get feedback on how well you're doing. The two are separated in the bioanchors work because the author wanted to impose specific beliefs on the effective horizon length, but was happy to continue extrapolating from current examples for noise. Subsection Field Building. Link AI Safety Career Bottlenecks Survey Responses by Linda Linsfors, summarized by Rohin. A past survey asked for respondents' wish lists for things that would be helpful and or make them more efficient with regards to careers in AI safety. This post provides advice for some of these wishes. If you're trying to break into AI safety work, this seems like a good source to get ideas on what to try or resources that you hadn't previously seen. Section Miscellaneous. Link Existential Risk from AI Survey Results by Rob Bensinger, summarized by Rohin. This post reports on the results of a survey sent to about 117 people working on long-term AI risk, of which 44 responded, asking about the magnitude of the risk from AI systems. I'd recommend reading the exact questions asked, since the results could be quite sensitive to the exact wording, and as an added bonus, you can see the visualizations of the responses. In addition, respondents expressed a lot of uncertainty in their qualitative comments. And of course, there are all sorts of selection effects that make the results hard to interpret. Keeping those caveats in mind, the headline numbers are that respondents assigned a median probability of 20% to X risk caused due to lack of enough technical research, and 30% to X risk caused due to a failure of AI systems to do what the people deploying them intended, with huge variation. For example, there are data points at both 1% and 99%. Rohin's opinion. I know I already harped on this in the summary, but these numbers are ridiculously non-robust and involve tons of selection biases. You probably shouldn't conclude much from them about how much risk from AI there really is. Don't be the person who links to this survey with the quote, "Experts predict 30% chance of doom from AI." Link, Survey on AI Existential Risk Scenarios by Sam Clark et al., summarized by Rohin. While the previous survey asked respondents about the overall probability of existential catastrophe, this survey seeks to find which particular risk scenarios respondents find more likely. The survey was sent to 135 researchers, of which 75 responded. The survey presented 5 scenarios, along with an other, and asked people to allocate probabilities across them, effectively conditioning on an AI-caused existential catastrophe and then asking which scenario happened. The headline result is that all of the scenarios were roughly equally likely, even though individual researchers were opinionated, i.e. they didn't just give uniform probabilities over all scenarios. Thus, there's quite a lot of disagreement over which risk scenarios are most likely, which is yet another reason not to take the results of the previous survey too seriously. Section AI Governance. Link, Some AI Governance Research Ideas by Alexis Kalia et al., summarized by Rohin. This is exactly what it says. Section Other Progress in AI. Subsection Deep Learning. Link, The Power of Scale for Parameter-Efficient Prompt Tuning by Brian Lester et al., summarized by Rohin. An earlier paper in this newsletter showed that prompt programming, as currently practiced, depends on having a dataset on which prompts can be tested. If we have to use a large dataset anyway, then could we do better by using ML techniques like gradient descent to choose the prompt? Now, since prompts are discrete English sentences, you can't calculate gradients for them, but we know how to deal with this. The first step of a language model is to embed English words, or syllables or bytes, into a real-valued vector, after which everything is continuous. So instead of using gradient descent to optimize the English words in the prompt, we instead optimize the embeddings directly. Another way of thinking about this is that we have our prompt be a sentence of, say, 50 completely new words, and then we optimize the meaning of those words such that the resulting sequence of 50 newly defined words becomes a good prompt for the task of interest. The authors show that this approach significantly outperforms the method of designing prompts by hand. While it does not do as well as fine-tuning the full model on the task of interest, the gap between the two decreases as the size of the model increases. At around 10 billion parameters, the maximum size tested, prompt tuning and model tuning are approximately equivalent. In addition, using a prompt is as simple as pretending the new prompt embedding is your input and running it through your model. This makes it particularly easy to do ensembling. If you have n prompts in your ensemble, then given a new input, you create a batch of size n where the ith element consists of the ith prompt followed by the input, and run that batch through your model to get your answer. In contrast, if you had an ensemble of fine-tuned models, you would have to run n different large language models for each input, which can be significantly more challenging. Section News. Link, AI Safety Research Project Ideas by Owen Evans et al., summarized by Rohin. In addition to a list of research project ideas, this post also contains an offer of mentorship and/or funding. The deadline to apply is June 20th. Link, Research Fellow, AI TEV&V, summarized by Rohin. CSET is currently seeking a research fellow to focus on the safety and risk of deployed AI systems. Link, Deputy Director, CSER, summarized by Rohin. The Center for the Study of Existential Risk, CSER, is looking to hire a deputy director. This concludes Alignment Newsletter number 152. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.